seems there's fewer of us than before. 17 was the one. Well, it's the same. Okay. Any questions about the homework? No? Okay. So what I'm going to talk about today is something called variational calculus. And this is an alternative way to derive Lagrange's equations. And after today, we're going to move on to the case where we have equations of motion with dissipation, with damping. But today is going to be the last day that we talk about sort of conservative systems. And so this is variational calculus. Better marker. Okay. And so I brought my extra markers last time, but there were all kinds of markers here, but this time there are no good markers. So hopefully this one will last us until the end of the class. What is this? I don't know if that's permanent or not, so I'm not going to try that on the board. Okay, so the idea of variational calculus, much like regular calculus, is that we have some quantity that we want to minimize or maximize. In regular calculus, so let's say classical calculus, what we have is some function, let's say f of x1, x2, up through xn. And if I ask you, how do you find the minima or maxima in a function like that? You know from your calculus class, multivariate calculus class, that you take your partial derivatives, set them equal to 0. Those give you some conditions. And so if you say, let's say that a particular value x prime, which has these components, x1 prime through xn prime, let's say that satisfies these conditions. That would be either a minimum, a maximum, or a point of inflection, a saddle point. Okay? And then we have, so these are necessary conditions for a minimum, but they're not sufficient conditions for a minimum. We'd have to go back and check the second derivatives. Okay? Well, that's classical calculus. In variational calculus, we have a different kind of problem. In variational calculus, we have an integral, I. Let's say we integrate from time 1 to time 2. We have a function that could be a function of time, could be a function of, let's say, x of t, and a function of x dot of t. And so, unlike the regular calculus that you're used to, variational calculus asks the question, how do we find a path in time? So if this is time, and this is x, and we have some initial conditions, say some boundary conditions, t1 and or I use t1 and t2 over here, and we have some initial value x1, which is x of t1, and then we have another value, x2 at time t2. So x1 is equal to x at time 1, x2 is equal to x at time 2. And the problem that we tried to solve in variational calculus is how do we find x of t that will satisfy these end conditions and will minimize this I. Okay, so that's the goal in variational calculus. So the goal is to find x of t that minimizes I while satisfying end constraints. Okay, so these are the end constraints. Let's call it star. Okay, so we want, if the goal in variational calculus is that we want to find x of t that satisfies these end conditions. It's a path that we're solving for, that when we substitute into this integral, we minimize I. That's the goal. Okay? That's the difference between regular calculus and variational calculus. In regular calculus, we're looking for a point. We're looking for a particular value of x that, when substituted into the function, minimizes the function. In variational calculus, we are trying to solve for a path, x of t, that minimizes an integral. Okay? Are there any questions about the goal of variational calculus? Now, it turns out variational calculus is an alternative path to Lagrange's equations. And what I'm going to do first is, so essentially what I'm going to do is derive what are the conditions that are similar to these conditions, except in the variational calculus context. So let's motivate the problem a little bit. So why would we care about a problem like this? Why would we want to minimize this kind of cost functional? So this we call a functional. It's not really a function anymore because we've integrated out all of the variables, but it's still something that we want to minimize. And so, for example, one kind of problem that falls into this framework is if I'm in the plane and I say, here are 2 points in the plane, and I ask, what is the curve connecting those 2 points that has minimal distance, minimal length? Okay. Well, we can formulate that as an integral, say, from x1 to x2, the square root of 1 plus dy dx squared dx. In other words, we can ask the question, what is the function y equals y of x that minimizes the contour length going from this point to this point? Okay, so you know, back in calculus, you learned that you can calculate the length of a curve using a functional like that. So that fits into this framework where here y is in place of x is in place of t. The dy dx is just like this term. This is a case where we don't have a y of x in the problem. And we don't have an explicit dependence on x either, so it's just like a special case of what we have up here. Now, so this is kind of maybe too easy of an example because we sort of know in advance that the straight line segment is the one that should minimize the distance between the 2 points. But if I gave you a similar problem where instead you have a surface and you ask what is the curve on that surface that connects 2 points, and the curve is inside of the surface the whole time, connecting the 2 points, and what curve minimizes the distance. So for example, if I give you a sphere and give you 2 points on the sphere and ask what is the curve that minimizes the distance between connecting the 2 points, that problem also is not too hard, but can be addressed using this methodology. If I give you some irregular surface, okay, an ellipsoid or the surface of a donut, a torus shape, and ask what curves connect those 2 points and have minimal length, this formulation can handle that as well. And then there's some problems outside of sort of the physical realm that also fall into this framework, and I know that we have some well, okay. Well, I'll come back to that example that I was thinking of later. So, okay, so here's how it goes. In variational calculus, what we do is we start with the assumption that a global solution, minimally, an optimal solution exists. So let's let capital Y be the optimal solution. So the picture looks like this. So in order to be a solution, we have to satisfy the end constraints. And let's say that this one is the optimal solution. And suppose then we look at small variations around that optimal solution. Okay, so we have an optimal solution and then we have variations around that optimal solution. So the way that that would be described, so all of these have to satisfy the end constraints. So here's, say, x1 and y of x1. Here's x2. And then this is y of x2. And so these variations, little y of x, and I'll call it x of alpha, has to be sort of this baseline one plus some alpha times a small amount, epsilon of x. So in other words, epsilon of x is describing how far we are varying around this global solution, this optimal solution. So we don't know what the optimal solution is. We're just saying, assume that it exists, and then let's look at small deviations around that and see what happens. So the conditions on epsilon are that epsilon at x1 and epsilon at x2 both have to be equal to 0 so that we satisfy the end constraints. If we don't have that, then we won't satisfy the end constraints because the capital Y satisfies the end constraints. And so when we add whatever perturbations to this that we're going to add, then we can't change the end constraints. But other than that, the epsilons are pretty much arbitrary. Okay. So then what we're going to say is, well, in order to be an optimal solution, what do we mean by an optimal solution? Well, it means that if we take this and we substitute it into our functional, and just for consistency, I'm going to keep with, instead of t's and x's, I'm going to keep with y's, and so x is the domain of integration, y of x, y prime of x, dx. So if we take this y and we put it in here, then the result, after we integrate out, all of the x dependence, is only going to depend on alpha, okay, which is the amount that we're perturbing from our globally optimal solution. Even though we don't know what capital Y is yet, if we did know capital Y and we substituted this in here, no matter what the epsilon of x is, after we integrate out, we're going to get that I depends on alpha only. Okay, so I of alpha is the integral from x1 to x2, f of x, and then it's capital Y of x plus alpha epsilon of x capital Y prime plus alpha epsilon prime dx. Okay. Now, what we can do, because so this is my I of alpha, and our goal, so the conditions, just based on classical calculus, the conditions for optimality, if I want to minimize I of alpha, what I'm going to do is I'm going to set di d alpha equal to 0. The added catch here, though, is that by definition, the optimal solution is when alpha is equal to 0. So when alpha equals 0, if I set this derivative equal to 0, that's going to be conditions on the optimal the optimal capital Y, which is what we get when alpha is equal to 0. So what we can do, there we go, thank you. So what we can do, maybe I'll switch now. Is do this computation on this integral. So if I take d alpha, that can come inside the integral. And the reason why it can come inside the integral is because the integral is over x, and alpha is independent of x. So when I bring that inside, I can use the chain rule, and the chain rule says that I'm going to get partial f, partial, okay, so where is the alpha? The alpha is here. So I have an f of x, y, y prime. So if I say what is the partial derivative of this with respect to alpha, there's an alpha here and there's an alpha here. So from the chain rule, it's going to be partial f, partial this place in the function, which is the y place of the function, times the derivative of the thing that's sitting in the y place of the function with respect to alpha, and that's epsilon of x. In other words, d alpha of this is just epsilon of x. Okay? Plus, and then the chain rule again continues as partial f, partial y prime, what's in the y prime place, times the derivative of what's in the y prime place with respect to alpha, which is this. Okay? So this is, again, a function of x. And prime here means derivative, right? Y prime is dy dx. Now, at the end of all of this, we have, we should set alpha equal to 0, because this is what we're calculating. But that can be done, that should be done at the very end. We don't, when we take a derivative and evaluate it at something, we don't first evaluate and then take the derivative, because once you evaluate something, you have a constant. It doesn't make sense to take a derivative after evaluating. You take the derivative before you evaluate at a particular value. Okay, now what we can do here is use the chain rule. I'm sorry, use we've used the chain rule already. We can do integration by parts to make these two things look the same. And so, what is integration by parts? Integration by parts, right? It's integral from, this is again just basic calculus, integral from A to B of u dv equals uv minus the integral of v du. And what we're going to do is we're going to focus on this term right here. And we're going to call, so we're going to call this one u. Can't draw a u today. Okay, let's try again. Here's u, and here's dv. Okay, so if this is u and this is dv, then that means that du is going to be dx of partial f partial y prime times dx, and v is going to be, so the dx is really part of this also, so let me rewrite that. So dv is equal to epsilon prime of x dx. The dx from here gets included in the definition of dv, and then v is going to be the integral of that, which is just epsilon of x. Okay, and so what that means is that this second part of the integral, which I'll write separately out here, this second part of the integral, so the integral from x1 to x2, partial f, partial y prime, epsilon prime, dx, by integration by parts, can be rewritten as u times v, so it's going to be partial f, partial y prime times epsilon, evaluated from x2 to x1, minus the integral from x1 to x2. Now it's going to be v du, and I've calculated that over there. So that's going to be d dx partial f partial x prime times epsilon of x dx. This epsilon of x, this is of x. Everything here is a function of x. And now, but remember what we said about epsilon of x. Epsilon at the endpoints has to be equal to 0, which means that this term disappears. And so then if we take this, which is just this right here, and we recombine it with this, what we get is that our d alpha is the integral from x1 to x2. The first term stays the same. It was partial f, partial y, and we have the epsilon of x out here, dx. And then the second term is minus d dx partial f partial y prime. Okay? And we want to set this alpha equals 0, and then this whole thing we want to set equal to 0 for our conditions for optimality. Now, we've seen several different times before in the class the concept of a localization argument, right? A localization argument was, I give you a times b equals 0, and for a sufficiently rich set of a's, if that's true repeatedly, then it must mean that b is equal to 0, right? And this is no different than that because the perturbations that we're doing here, the variations around the optimal, the assumed optimal solution are arbitrary. What we're doing is sort of kicking the tires, so to speak. You know, here's the optimal, you tweak it over here, you tweak it over there, vary it in all kinds of different ways, and see what happens. And so the point is that because this guy is arbitrary, if I take an integral of something times an arbitrary function, and that has to be 0 all the time, then the thing that's inside the brackets here, that's multiplying that arbitrary function, itself has to be equal to 0. Okay? So in other words, because this is true for all possible epsilon of x, then that means that this thing that's inside the integral has to be equal to 0. And that quantity inside of the integral is partial f partial y prime minus d dx partial f partial y is equal to 0. Okay? Now, this should look familiar for two reasons. Yes?
Did you flip the primes?
Flip what? Oh, there's a prime here. Oh, yeah. Why did I do that? Okay, thank you. Okay, so this should look familiar for two reasons. First of all, if I give you f of, let's say, x, y, y prime, and if there's no dependence on x, and if there were no dependence on y prime, then this term would disappear, and I would get partial f partial y equals 0. Well, that just looks like the usual conditions for a minimal solution in calculus, right? That's one reason why it should look familiar. So in other words, the variational part gives us this second term that we don't usually see in regular calculus. The other reason why it should look familiar is because this is basically Lagrange's equation. With instead of x, if you had a t, and instead of y, you had a generalized coordinate, and instead of f, you had the Lagrangian, which is kinetic minus potential energy, then this would be exactly Lagrange's equations. So, and in fact, this form is called the Euler-Lagrange equations. And this is for the case where you have a single scalar function y. If I gave you x and y1, y2, y3 up through yn, and y prime 1 up through y prime n, then you would get multiple equations here, just like in Lagrange's equations. But this is a single Lagrange equation. Okay, so let's try to use this. And we'll go back to the example that I mentioned, which was, suppose that you have I is the integral from x1 to x2. So it's the arc length of a planar curve. Okay, so this is y prime right here. And we substitute into that equation. We have end conditions. We have, y of x1 is given. We'll call it y1. And y2 is y of x2. And let's substitute into that equation and see what we get. Okay? So my f here is the square root, which I'm going to write as the 1/2 power of 1 plus y prime squared. Okay, so in this case, partial f, partial y is equal to 0. Right? There's no explicit dependence on y, it's only dependence on y prime. So this term goes away, and we get this, but that tells us that, that this quantity right here has to be a constant. So the Euler-Lagrange equation reduces down to partial f, partial y prime is some constant. Okay? So if we calculate then what is partial f, partial y prime, what we get is 1/2 times what's inside to the negative 1/2 power times the derivative of what's inside, which is with respect to y prime, which is 2y prime. And that has to be equal to some constant. Okay? So what we can do is then rearrange this and find out what y prime has to be. So we can multiply both sides by the reciprocal of this. So we get 1/2. Well, first of all, the 1/2 and the 2 cancel. The 2 and the 1/2 cancel. So we get y prime is equal to some constant times 1 plus y prime squared to the 1/2 power. We can square both sides, so we get y prime squared is equal to c squared times 1 plus y prime squared. So, and then we can isolate the y prime on one side of the equation, so we get y prime squared, that's 1 minus c squared times y prime squared is equal to c squared. So we get y prime squared is equal to c squared over 1 minus c squared. So basically what that says is that y prime is another constant. We'll call it a. This c was some constant, an arbitrary constant. We can call it a squared if we like.